Hello, this is Dr. Jae Shin, who graduated from Hanyang University under the guidance of Professor Park. After graduation, I worked for the Hyundai Steel R&D Center for 3 years until 2020. And now I'm working for the Korea Institute of Industrial Technology. Today, I will talk about effects of CaO alumina ratio of the slag on the formation behavior of inclusions in the aluminum clad molten steel, which started with the Professor Park when I was in the Hyundai Steel. Introduction. As you know, the special steel has been widely used as automotive parts, such as heel hub, con rod, crankshaft, and etc., since that has good mechanical properties. However, the final product performance can be significantly affected by steel cleanliness. Especially, the high hardness inclusions such as spinel or alumina inclusion potential cause not only surface defect of final products, but also nose clogging during the continuous casting process. These inclusions are formed by slag, metal, refractory multi-phase reactions during the lead refining process. Hence, it is very crucial to predict and control the inclusion composition during the lead refining process. Thermodynamics of the formation behavior and modification of spinel inclusion in molten steel have been extensively investigated since the 1980s. Specifically, Park et al. Reported that the formation mechanism of spinel inclusion during the stainless steel refining process. In addition, many researchers have investigated the effect of calcium treatment on the modification of alumina and spinel inclusion to improve the castability during the continuous casting. Recently, Verma et al. Reported a mechanism of direct calcium treatment to modify alumina and spinel inclusion. More recently, the simulator to predict formation of inclusion during the slag metal reaction have been developed by several researchers. Our research group also developed the refractory slag metal inclusion multi-phase reaction model to predict and understand inclusion behavior during these multi-phase reactions. In addition, it was reported that the effect of indirect calcium treatment by slag metal reaction on the modification of inclusions. And we emphasize the importance of slag composition to control the inclusion. Therefore, in the present study, we investigated the multi-phase reaction among aluminum-clad steel mat and lead slag and MgO refractory using high temperature experiment and RSMI reaction simulator to understand the evolution mechanism of inclusion and to understand the effect of basicity of the slag on the formation behavior of inclusion. And finally, we will propose the optimum range of the slag basicity to suppress the harmful inclusions. To confirm inclusion behavior in molten steel during the slag metal refractory multi-phase reaction, we conducted high temperature experiment using high frequency induction furnace. On the argon atmosphere, I melted steel at 1873 Kelvin and added Fe aluminum alloy into the molten steel to control the initial aluminum content. After 30 minutes, the pre-melted slag was injected throughout the Koch tube. After certain injection period, I quickly taken steel and slag samples using Koch suction tube and steel rod respectively. The CaO alumina ratio of the slag was varied from 0.9 to 3.3 in order to confirm effect of slag basicity on inclusion behavior. After experiment, the steel sample were prepared for chemical analysis, and automatic feature analysis with SAM-EDS system was employed to obtain inclusion information such as composition, morphology, and population statistics. Firstly, I will talk about change in slag metal inclusion during the multi-phase reaction. This figure shows the change in the content of each element of molten steel by refractory slag metal multi-phase reactions. Immediately after the addition of the slag, the oxygen content drastically decreased to about 10 ppm, and aluminum content in the molten steel gradually decreased while silicon content slightly increased. This tendency originated from the reduction of SiO2 in the slag by aluminum in the molten steel, as given in the following equation. The magnesium and calcium were also transferred from slag to metal phase by this equation. In case of the slag composition, the change of MgO content in the slag during the reaction is shown in this figure. The MgO content in the slag increased with reaction time, which originated from a chemical dissolution of MgO from refractory to slag. It is certain that the amount of MgO dissolution increased with decreasing CaO alumina ratio of the slag. Although MgO was not saturated in the initial slag, the MgO was finally saturated by dissolution of the MgO from refractory to slag during the reaction. This was confirmed by XID analysis. When the CaO alumina ratio of the slag is 0.9, only the MgAl2O3 spinel peak was detected before the refractory slag metal reaction, which was also expected from the phase diagram. However, MgO and the spinel peak coexisted after 9 minutes since the slag metal refractory reaction started. When CaO alumina ratio are 1.2 and 1.6, although the initial slag was fully liquid, MgO was finally saturated by slag metal reactions. The MgO peaks were detected both initial and final slag when CaO alumina ratio of the slag was higher than 2.0, which was expected from phase diagram. That is, the activity of MgO in molten slag converges to unit. Consequently, magnesium and calcium are transferred from slag to molten steel. This change of metal and slag composition caused the modification of inclusion during the slag metal reaction. So we observed the inclusion change by using automatic feature analysis with SAM-EDS system. Firstly, when CaO alumina ratio of the slag are 0.9 and 1.2, the initial inclusion was mainly alumina, which originated from aluminum deoxidation. After 5 minutes, some of alumina inclusion transformed spinel and liquid oxide inclusion, and the fraction of spinel inclusion increased and then decreased. Consequently, the spinel inclusion and liquid oxide inclusion coexist in the molten steel at the final stage of the reaction. On the other hand, when CaO alumina ratio are 1.6 and 2.3, the most of alumina inclusion modified spinel and liquid oxide inclusion. However, the spinel inclusion disappears after the 30 minutes. Consequently, only liquid oxide inclusion exists in the molten steel at the final stage of the reaction. Finally, when CaO alumina ratio is 3.3, the fraction of spinel inclusion continually decreases until 50 minutes. 30 minutes after the reaction started, spinel inclusion transformed to MgO inclusion in the molten steel. The relative fraction of MgO inclusion increased up to 50% until the final stage of the reaction. Well, we conducted thermodynamic analysis to confirm effect of activity of slag component on formation behavior of inclusions. The activity of components in the initial slag and final slag were calculated by using package software. The MgO activity and CaO activity in the initial slag increase with increasing CaO alumina ratio of the slag. Especially, the MgO activity is unit when CaO alumina ratio of the slag higher than 2.3. On the other hand, the activity of alumina and SiO2 decreased with increasing CaO alumina ratio of the slag. A difference in the activity of CaO, Al2O3 and SiO2 between initial and final slag is very small. However, there is a significant difference in the MgO activity between initial and final slag when CaO alumina ratio lower than 2.3. That is, the MgO activity converts to unit at the final stage of the reaction. The relative fraction of each inclusion type at the early stage of the reaction as function of CaO alumina ratio is shown in this figure. Also, the activity of CaO increased with increasing CaO alumina ratio. The spinel inclusion increased with increasing CaO alumina ratio of the slag. This means that the influence of MgO activity on the formation tendency of inclusion is higher than that of CaO. That is, this reaction is more dominant than this reaction at the early stage of the reaction. On the other hand, the fraction of spinel inclusion at the final stage of the reaction decreased by increasing CaO alumina ratio of the slag. Alternatively, MgO inclusion was formed in the molten steel at the CaO alumina ratio is 3.3. Also, the MgO activity is unit regardless the CaO alumina ratio. The spinel inclusion decreased by increasing CaO alumina ratio of the slag. This means that the influence of CaO activity on the formation of inclusion is greater than that of MgO. That is, this reaction is more dominant than this reaction at the final stage of the reaction. I calculated the activity of magnesium and calcium in equilibrium with the final slag as follows. The activity of magnesium and calcium increased with increasing CaO alumina ratio of the slag. When CaO alumina ratio of the slag is 3.3, MgO inclusion was formed. Also, the calcium activity is highest. This phenomenon can be explained by following discussions. The critical activity of magnesium to form MgO inclusion can be calculated based on this equation. The critical activity value to form MgO inclusion is shown in this figure, the open scales. As shown in this figure, the magnesium activity in the molten steel is higher than critical magnesium activity at the CaO alumina ratio is 3.3. Result in the formation of pure MgO inclusion. We confirmed the relationship between slag basicity and inclusion behavior by using high temperature experiment. Next, I will tell you about simulation result of inclusion prediction using RESMI reaction model. We developed the RESMI multi-phase reaction model by adapting effective equilibrium reaction zone concept and using the hexadecimal processing. I set the simulation variable the same as the experimental conditions. As shown in these figures, we can confirm the calculated results are in good agreement with the experimental results. It is interesting that the magnesium and calcium pickup from slag to metal phase is predicted to increase from 7 ppm to 11 ppm and from about 1 ppm to 5 ppm, as the CaO alumina ratio of the slag increases from 0.9 to 3.3. Because the effect of magnesium and calcium on the stability of inclusion in the steel mat are significantly meaningful, a phase stability diagram of the inclusion in aluminum-cured steel mat containing magnesium and calcium is usually calculated with an aid of hexage. These symbols represent the magnesium and calcium trace in molten steel according to the reaction time, which calculated using the RESMI multi-phase reaction model. When CaO alumina ratio of the slag lower than 1.5, the alumina inclusion is stable at the initial stage of the reaction. However, the stable phase changes from alumina to spinel within 3 minutes, and still remain in the spinel predominance area throughout the entire holding time. However, when the CaO alumina ratio of the slag are 1.6 and 2.3, the stable phase rapidly changes from alumina to spinel within 1 minute. The evaluation trace of the inclusion follow the dashed line with an increase of calcium content for about 10 minutes, after which trace get into the liquid inclusion predominance area and then remain until 90 minutes. Finally, when CaO alumina ratio is 3.3, the calcium content is predicted to exceed the threshold of the spinel liquid transition within 3 minutes. But magnesium content also exceeds 10 ppm at about 50 minutes. And thus the evolution trace cross the phase boundary from liquid oxide to MgO predominance area. Summary and conclusions. We investigated a multi-phase reaction among aluminum-cured steel melt, lead slag, and MgO refractory using high temperature experiment and RESMI reaction model to understand evolution mechanism of the inclusion and to understand effect of basicity of the slag on the formation behavior of inclusions. As a result, we can conclude that the formation behavior of inclusion could be divided into the 3 cases with the CaO alumina ratio of the slag as follows. Therefore, I recommend that the CaO alumina ratio of the slag should be controlled from about 1.5 to 2.5 in order to suppress the harmful spinel inclusion during the lead refining process. Thank you for your attention.